Good afternoon, ladies and gentlemen. We are very pleased to join the OpenStack case showing event. And we are about to share the pulpit with China's largest OpenStack Cloud, accelerate the science discovery of AMS-02. First of all, I would like to introduce the speakers. As the cloud computing manager of Southeast University, Mr. Zhang Jinghui, we introduce the Southeast University with AMS-02 and tell you why they chose OpenStack. In addition, we also have another two speakers. My name is Li Honghui. I come from Chinese OpenStack company OpenStack, and I'm the telecom manager of East China. I will tell you the solution based on OpenStack. And Mr. Fan Jibiao is come from Chinese company Aogong Technology. He is responsible for developing, and he will tell you the key points of Southeast University's architectural design. At last, Mr. Zhang will answer your question if necessary. Well, this is the four parts I just mentioned. Part 1, about SEU and AMS-02. Part 2, why OpenStack? Part 3, solution based on OpenStack. And part 4, key points of architecture design. Now, welcome Mr. Zhang to introduce the first and the second parts.
So good afternoon, everyone. My name is Jing Hui, and I'm from Southeast University. I'm the cloud manager of this university, and I'm also the assistant professor at the School of Computer Science and Engineering of Southeast University. So our university is a public research university located in Nanjing, China. Maybe some of you have been to Nanjing, maybe not. So Nanjing is the provincial capital of Jiangsu province, and it's like 300 kilometers from Shanghai. So if you take the high-speed train, it will take like 1 hour to get from Shanghai to Nanjing. So, our university is a member of both project 985 and 211. It's the top university league of China, much like, Ivy League of the US or the Russell Group of the UK. And recently in October this year, Chinese government and the Ministry of Education of China, they announced a new program. They just selected some universities to be, world-class universities. So our university was selected into, this program. And according to this year's U.S. News University ranking, our computer science was ranked as the 20th of the best global universities. And our engineering was ranked 27th in best global universities. So, as Honghui just mentioned, our topic is to discuss the OpenStack Cloud and to accelerate the science discovery of a scientific experiment, which is called Alpha Magnetic Spectrometer, aka AMS. So AMS is a high-energy physics detector, which is mounted on the International Space Station. It will collect data of particles from the outer space, and scientists will try to analyze the data and make science discoveries. So AMS, is U.S. Department of Energy-led international collaboration. In fact, it is a very large collaboration. We have, scientists from 16 countries, 60 institutes, and we have like 600 physicists involved in this experiment. So this experiment has been going on for like 20 years, and we have invested like $2 billion on this experiment. And the principal investigator of the experiment is a Nobel Prize winner, Samuel Ting. He's currently a full professor at MIT, and he just leads our experiment. And our university, Southeast University, we joined this AMS experiment ever since 2002. and we are the first Chinese university to join this experiment. So, the first major purpose of our experiment is to search for the existence of the antimatter universe. So many of you may have already heard a theory. It's quite popular in physics. It's called the Big Bang theory. So the Big Bang origin of the universe requires matter and antimatter to be equally abundant at the very hot beginning. So it means that if we have the universe, we should have also an anti-universe. So for example, if we everybody here knows that we have an electron, so there must be some anti-electron in the universe, right? So this is the first major purpose of our experiment. The second purpose of the experiment is to identify the origin of the dark matter. The data shows that more than 90% of the universe is not visible, and we call them dark matter or dark energy. So as shown in the picture, you can see that if we could see a dark matter in the galaxy, then the current universe that we can detect using telescopes should be very, very small. So this is the second purpose of our experiment. So just a very short summary. Our experiment was to search for antimatter, the origin of dark matter and dark energy. So you can see the picture. Our detector was just installed on the International Space Station. So maybe the picture is a little bit small. So our AMS is the only large experiment that searches for dark matter in the outer space. So let's have a closer look. So this is a big picture of our experiment. So it's like 7.5 tons. We have multiple sub-detectors in this detector. We have like a transition radiation detector, we have time of flight detector, we have magnet, we have rich, and we have echo. So each of the detectors, they just measure the different properties of the particles that passing through the detector. For example, like mass, like energy, and etc. So a combination of these multiple sub-detectors, you can uniquely identify the particle that is passing through the detector. So for the electronic part, we have like 300,000 electronic channels, and we have like 650 microprocessors. So this is a real, expensive instrument. So since we need to install the detector on the International Space Station, so we need some kind of transportation, right? So we have to pre-install the detector in the Space Shuttle in Denver. So this is how it looks like. And this is when we just make the launch of the Space Shuttle. It was launched on May the 16th, 2011. And in fact, it's the very last mission of the Space Shuttle in Denver. After that flight, the Space Shuttle in Denver just retired. So it's his last mission. And after 3-day flight, the Space Shuttle just arrived at the International Space Station, and the detector was just installed there. It's on May the 19th. So after that, data taking just began. So this shows the data flow. The most important thing is data, right? We just install it on ISS, and then we get data. So here's the data flow. When we collect the data, of the particles that are passing through the detector, the format was just some raw data frames. So these data frames will be transferred to the ground by satellites, and the data will be transferred to Marshall Space Flight Center first, and then the data will arrive at JSC and CERN, European Organization of Nuclear Research. In fact, CERN is the headquarters of our experiment, so we have a lot of data centers there. So the data will be stored and analyzed in both POC and SOC. So POC here stands for Payload Operation and Control Center. It means that we can both do monitoring and commanding from the POC. We can check the status of the detector, and we can send commands to change the status of the detector. That's POC. And we do a lot of data analysis and data processing in SOC. SOC stands for Science Operation Center. So since the CERN is the headquarters, so we have both SOC and POC here. And we also have a lot of regional data centers. Our university, SCU, is just one of the remote data centers. So we do a lot of data processing tasks like data storage, data analysis, and physics analysis, something like this. So here's a picture of the POC at CERN. So you can see it's located in Geneva, and we have a lot of desktops, and each desktop is just responsible for monitoring one of the subdetectors. For the SOC, this chart shows the data flow. So when we get the data from the outer space, it's in the format of frames. Then we will do some pre-production, and then after this pre-production, we have raw data. So this raw data will be used in our SOC. Then we will do a lot of analysis and data processing. Then it will be changed into the format of root files. So the root files are quite familiar, to those physicists. It's a common format that physicists can just, use it and do analysis. So after doing this computation, we needed to transfer all these root files to the headquarters. To the cluster storage system at CERN. So this is a kind of data processing flow. Except, besides the data, we also have metadata. So these metadata are just automatically generated. So they will be used for simulation. So we have the real data and we have simulation data. So we just use this both data to do physics analysis. So question comes. So why do we need an OpenStack, right? We just maybe you're just wondering why. So I will introduce why. So why do we need OpenStack at SCU's AMS SOC? So the first reason is that we need a hybrid cloud. So for AMS data processing, we know that it's quite data and computation intensive. So we typically just use high performance computing, right? So we just use physical servers. We just use shared storage. We use a parallel file system. We use batching job schedulers, right? This is a typical scenario. But for AMS, from time to time, we will have peak periods that demands a lot of computation resources. So, but after this peak hour, maybe we just don't need that more. So, Elastic Cloud just perfectly match the such kind of demanding pattern of computing resources. That after this peak hour, we can just release those resources and just put it in a big sharing pool, right? So this is why we just need a cloud. And on the other hand, since we are from the university, so we have lots of departments, and they just need a different operating system. They need to install different software, and they just need to put different applications on machine. So in this scenario, OpenStack Cloud could provide VMs, a lot of VMs to our users, and they just satisfied with that. So this is the first reason that we need OpenStack. We need a hybrid cloud, and the second reason is it's much research oriented. So in university we need to do a lot of research. So OpenStack Cloud just provides a basic platform, a lot of VMs. Then we can do a lot of research based on this VM. For example, like VM management. We do a lot of research on VM migration, like green cloud. Like, we can just turn off some VMs and save energy, right? So this is also some kind of research. And we also do researches on network management, like SDN, like data center networking, like flow scheduling. It's quite popular in computer science. And we also do a lot of researches based on big data, right? So we can, based on those VMs, we can set up our own big data platforms like Hadoop, Spark, Storm, something like this, and we can do researches on big data platforms like scheduling, task scheduling, and resource management. So this is the second reason why we need OpenStack in our SOC. So this is a picture of our university's data center. So in fact, it costs us like 45 million Chinese yuan up to now. We have like 500 servers, and we have 2 petabytes of storage. yeah, that's kind of the scale of data center. And this is a server that we recently just built. It was built in this year's August or September. It has 3,000 cores and 1 petabyte of storage. And this is the old one. It has like 500 cores and almost 1 petabyte of storage. So this is a picture, the principal investigator of our experiment, the Nobel Prize winner, Professor Ting, just visited our university. And just besides him, he's the dean of a school of computer science and engineering. This is, what we have done. Based on the support of OpenStack, we have done a lot of data processing for AMS. In fact, we have processed more than 2 petabytes of data and contributed more than 30% of the total CPU time in the worldwide AMS data processing. And currently, we ranked the first among all the 18 regional AMS data centers worldwide. And the OpenStack Cloud really helped to accelerate the science discovery of AMS. And in fact, we have published 8 papers in Physical Review Letter, which is a top journal in the community of physics, and 6 of them are selected as editor suggestions, and we even have 1 or 2 as cover paper of this renowned journal. So based on OpenStack, we also established the first IBM-sponsored joint cloud research center in China, and our focus was on OpenStack-based VM performance measurement and hybrid cloud performance tuning. So this is also the first, this is the first Chinese joint research lab with IBM on cloud, based on cloud. So I guess that's all what I introduced. So next will be presented by Honghui. Okay.
Okay, thank you, Mr. Zhang. Then I will tell you the part 3, solution based on OpenStack. SEU's OpenStack Cloud architecture design includes 3 layers: the resource cluster, OpenStack, and application. As we know, OpenStack is module design. It includes many modules, and each module's communication with API. So we can choose the modules across to our need. In the application part, we can say the SEU's cloud need to provide service for AMS sense discover, and need to provide service for machine simulation, 5G communication simulation, nano simulation, semi simulation, and so on. So we need many kinds of resource. And at a resource cluster layer, we can see high-performance computing, virtual machine cluster, high-speed file system, SD network, and connect cluster and big data cluster. So we can provide and manage all of those resources on one platform. Maybe only OpenStack can do this. So let's see the part of the OpenStack. We chose Ionic to manage bare metal because the high-performance computing need to run on the bare metal. And we also run high-performance computing on the virtual machine. Mr. Fan Jibiao will tell you the solution. We chose NOAA to manage virtual machine cluster, and the virtual machine run on KVM. We chose Thunder to manage storage, and we use IBM GPFS file system. The GPF file system I/O is over 17 GB per second. We chose Neutron to manage network, and use the network solution based on Perl software in this project. And we use Magellan to manage container, use Hara to manage big data. In the monit and mid part, we provide virtual and physical monit includes VMs, cloud volumes, subnets, and physical control, compute network, and storage nodes. Tencents can define items and triggers. You can also enter them logs for troubleshooting. And the cloud security system part runs through the while SEU's cloud. So let's see a summary. Let's see the summary of the SCU's cloud. Based on OpenStack ES Cloud, SCU SOC has become one of the largest AMS data center and reaches the scale of over 500 servers and 2 PB storage. SCU has processed over 2 PB AMS data and contribute 30% of the total CPU times in AMS data processing. SCU correctly ranks #1 among all 13 regional AMS SOC worldwide. 18. And its OpenStack Cloud has accelerated the census cover of AMS. SCU has planned the extension of OpenStack's development to 5,000 more CPU cores next year. Okay, next, welcome Mr. Fan Jibiao to tell you the key point of architecture design.
Okay, in the first part, I will introduce the key technology of Southeast University Cloud Platform. There are 500 nodes from the SEUS Cloud. In total, there is 1 OpenStack cluster and 2 high-performance clusters. In order to achieve better expansion and high performance, we designed in the following ways. For the 3 control nodes, we apply OpenStack API and high available mode. Also, we use MySQL cluster as the database for the cloud platform of Southeast University. There are 200 OpenStack computer nodes for the scientific research and particular application in the university. We also use Ironic service to manage as many as 300 servers, which are used for AMS scientific findings. The Southeast University Cloud applies GPFS file system to OpenStack and HPC. The reading and writing ability is about 13 GB per second, and the volume is as much as 2 PB. In order to achieve high performance network with a low latency and high bandwidth, we choose the SDN technology of Mellog's network card and get rid of the performance loss caused by vSwitch. Apart from using the semi-virtualized network card, we apply SRIOV technology in the Neutron framework to use InfiniBand network. As a result, no matter it is a virtual machine or a bare metal node, RDMA protocol applies to them. It is much beneficial for the high performance cluster floating point calculation. In order to achieve HPC cluster file system and the OpenStack file system with the high reading and writing ability, we apply GPFS as the only file system. Distributed token management is applied inside GPFS through token manager server. The access to data requires Unicode authorization. The authorization of data access can be of the data block level. GPFS provides the standard file system and PostGIS interface, as well as the storage ability of GPFS as the glance service, sender service storage ability, and storage ability of virtual machine in OpenStack. In the meanwhile, it also provides experimental node with high efficient storage ability. For the testing SEUS Cloud platform, we used the following tools. Tools for testing implement network speed, and tools for test implement RDMA protocol latency, and used for testing the floating point performance of high-performance computer system benchmark international. And we use a network performance testing tool. The benefits of result. Through the IBVT, there will be one IB card virtualized to multi-blocks, mapping the virtual IB card to the cloud host through SRIOV. The IB delay is equivalent to the physical machine performance. The linpack performance of single node is more than 19%, which is close to the physical machine performance. Multi-node linpack for the multi-up physical machine. Parallel test of linpack, the performance is about 18%. Through the cloudy host pretell way. In the test, the linpack performance can reach 72% with the loss of less than 10%. This is my all speak. Thank you.
Okay, this is all speak. Thank you.
So if you have any questions, you can just welcome. You're welcome. Okay.
Okay.
You mean for the physics part?
The energy consumption computations, do you have any of those?
Yes, we have published some paper, but because it's not my work, it's the work of my team, our research team, so I don't have it on my hand. If you're interested, I can send it to you maybe later.
I'm referring to the cluster energies, not the computational energies.
Uh-huh.
The energy consumption by the HPC.
Uh-huh. You mean okay. I will ask my colleague. Okay. 他就是想问就是能耗方面，就是你那个虚拟机整个的集群测试时候有没有什么能耗的结果？
这个是没有的，但是它不会就是能耗这块没有。
So we didn't any test on efficiency. Yeah. Okay. Okay. So that's all. Thank you, everyone.